All right, so last time we talked about finding solutions to the characteristic equation, which was what mathematically we call the homogeneous case, the case where it's equal to 0. So I kept writing this notation, y sub c, to stand for that solution to the characteristic equation, and we ultimately found solutions to y of t as well. When it's equal to 0, that's all that I had. So today I want to think about getting this, what we call the particular solution, or even a complete solution to a differential equation. And our method, we have two methods for doing that. The first one we're going to talk about this week is the method of undetermined coefficients. So each time that we talk about or try to find a solution, y of t, we've got to find the solution to the characteristic equation. That's relatively easy. Those always became a quadratic or something of that nature. And we talked last time about the possibilities for those solutions. So two distinct roots, a repeating root, or an imaginary root, and how we represented those. And then today what I want to do is to find this piece, the particular solution for that particular equation. So with that in mind, let's look at a couple of examples. Number one says y double prime plus 3y prime plus 2y equal to 10e to the 3t power. So the first thing that I'm going to do is to find the solution to the homogeneous case. So let me come in here and look at this problem. Which factors into r plus 1 and r plus 2. And I end up with solutions of -1 and -2. So for my characteristic equation solution, we end up with some constant e to the -t plus some other constant e to the -2t. All right, so that becomes significant for us. I've got to kind of think about all of this stuff going over here on the right-hand side in light of these things. So I want to build some possible solutions to the right-hand side. So we examine those functions, and there's only a small family of functions we can apply the method of undetermined coefficients with. We want things whose derivatives are predictable. So, for instance, a polynomial, those derivatives are predictable. T squared becomes a t, becomes a constant. T cubed becomes t squared, becomes a t, becomes a constant. E to a power, when I differentiate, I always get back e to a power. Sine and cosine are pretty predictable, right? The derivative of sine is cosine. The derivative of cosine is negative sine. So those are things that I can kind of keep manageable. I know where their derivatives are going, and I can account for all possible solutions there. So for this problem, I want to build, I'm going to call it S, for a set of possible things based on this function. So e to the 3t, and that's going to be the only thing in the set. Every time I differentiate an e to the 3t, I get back an e to the 3t. So that's all I need to account for. So let me just pull over and think about families of things. So if I have an e to the t, then that set is going to be an e to the t. If I have a sine or a cosine, and it can be the sine of, 2t or something of that nature, then my set has sines and cosines, or sines of 3t's and cosines of 3t's in them. If I have some polynomial, then my set is going to have perhaps a t squared. Maybe the original solution might also have had a t in it. We just don't know. All right, so again, these are common cases, and again, they can be expanded upon. If I've got a 3t or 4t or whatever going on with those as well, we account for them. We can allow for that, okay? So what I'm going to do is, with all of the things in my set, I want to build a linear combination. And I'm fortunate here because the only thing in the set is an a to the 3t, okay? I'm trying to find the value of this a coefficient is ultimately what I'm going to do. Remember, this is the method of undetermined coefficients. Now let me differentiate. So the derivative of a constant times e to the 3t, the derivative of e to the 3t is 3 times that constant, and I get the 3t back. And then the second derivative is going to be 9e to the 3t. So what I want to do is to take all of those values and plug them into my original differential equation. Try to get that on the screen where we can see all of that at one time. So I'm going to plug in y double prime. I'm going to plug in 3 times y prime. And I'm going to plug in 2 times y. And I'm going to set it equal to this 10 e to the 3t portion. That's our plan. So here we go. Y double prime plus 3 times y prime. And then plus 2 times y. And I want all of that equal to, my apologies for the shift, 10 e to the 3t. So let's simplify and see what works out. So I have a 9e to the 3t plus another 9ae to the 3t plus a 2ae to the 3t, all equal to 10e to the 3t. And all of these are like terms, so I can combine. So 9 and 9 is 18 plus 2a is 20a e to the 3t. And so really, I'm going to equate coefficients at that point. So 20a is equal to 10a must be 1/2. So my particular solution to this problem is 1/2 times e to the 3t power. Now keep in mind that our general solution is the characteristic equation solution, which was this plus the particular solution portion. So that is the solution to the differential equation. These are not bad problems, y'all. The only trouble you're going to have here is taking all those derivatives, because they can get involved pretty quickly. We know this has to be part of the solution because that's the case where it's equal to 0. So 0 plus this is going to provide for me that original solution. And given some initial conditions, I haven't assigned any problems like this, but given some initial conditions, we can go back and find values for C1 and C2. Let's look at a second one, example 2. Let's do y double prime plus 3y prime plus 2y, that's the same left-hand portion I had before, equal to the sine of t. So I already know the characteristic equation solutions. We just solved that and found those. So what I want to deal with is the particular solution portion. So let me find this set based on the sine of t. So again, I just have to allow for the possibility of everything. So I know there needs to be a sine in there, but I don't know that there couldn't be a cosine. Why do I need the cosine part? Keep in mind when I differentiate, the derivative of cosine is providing for me a sine. So that's where I can come back and find these values for this original sine t. And so I want a linear combination of those. So a sine t plus b cosine t. And I want to differentiate. The derivative of sine is cosine. The derivative of cosine is negative sine. And I need a second derivative as well. So the derivative of cosine is a negative sine. And the derivative of sine is cosine. So let's plug all of that into our original problem. So I have y double prime plus 3 times y prime, and I'm going to do that multiplication as I go. So plus 3 times y prime and plus 2 times y. And I want all of that to equal to the sine of t. And so sometimes we're in luck and some things will cancel themselves out, but absolutely I see some like terms. So I've got an a sine t and another a sine t. I've got some, what else do I have? Some b cosine of t's. Actually, let's lump all the let's do all these sines of t like I've started out doing. So yeah, let's find everything with a sine t in it, and then everything with a cosine. I'm hesitating because typically we would have maybe a cosine function over on this other side, and I don't, and that's okay. So if I take all of these sine functions, so I have a negative a, I've got a negative 3b, and a plus 2a, all times the sine of t. And I want to set that equal to the sine of t from this piece. And at the same time, I've got some cosine functions. So I've got a negative b, a positive 3a, and a plus 2b. Cosine of t. But I have no cosines on this other side. And that's okay. I just need to account for it. Alright, so this gives me, I'm going to combine these like terms. So this is a minus 3b equal to 1. Where did the 1 come from? The 1 is the coefficient sitting right here. And on the other side, I've got 3a plus b all equal to 0. I don't know why I put parentheses there, but it doesn't matter. All right, so you can use your favorite method for solving systems. I guess since this one is equal to 0, it would be pretty convenient to maybe use substitution, but you can use elimination, you can use Cramer's rule, whatever your method is. So I'm going to take that and plug it into this other problem. So a minus 3 times b, and I claim that b is a negative 3a. So that's a plus 9a equal to 1. Looks like a is 1/10. So I'm going to plug that back in over here. So b is a negative 3/10. So I'm ready to write my solution set finally. So my particular solution to this problem is a sine t plus b cosine t, and then my general solution is the characteristic equation solution plus the particular solution portion. So again, the only thing that's happening on these, let me move that way up where you can see that solution. Again, the only thing that's going to happen is you might have some tricky solving to do. Most of the time that is going to work out pretty nice, but here was a system and it's okay. And those derivatives can cause you some grief. And the sum total of this is the solution to the entire problem, that general solution.